In this video, we're going to introduce chapter 28, which is on magnetic fields. So let's talk a little bit about the source of a magnetic field. So a magnetic field can be produced by a bar magnet. So this is an example of a bar magnet. You can see that the magnetic field lines are always arranged in such a way that they point from the north to the south. So this example shows you the magnetic field patterns of a bar magnet. So you can see this is just a single bar magnet. So this is the north and the south. Magnetic field lines pointing from north to south. Now these are two bar magnets placed close to one another. So this is the north and this is the south. You can see magnetic field lines going from north to south. So there is an attraction between the two magnets. If this is a north and this is a north, then notice that because this is north and this is north, there is going to be some repulsive forces between the two magnets. So again, if you have a north and a south, you have an attractive force. If you have a north and a north, you have a repulsive force. So again, if you remember, we said that if you have a positive charge and a negative charge, you get attractive force. You have a positive charge and a positive charge, you get a repulsive force. And we also said that electric field lines always point from the positive to the negative. And so this is pretty much the same thing here. So magnetic field lines are always going to point from the north to the south. Now this example is an example of magnetic field in nature. So this is an example of the magnetic field that is produced by the Earth. So the Earth itself can be considered as a giant magnet. So it produces a magnetic field, and this is the north and this is the south. Again, you can see the magnetic field lines pointing from the north to the south. All right. So at this point now, we're going to look at a particle in a magnetic field. So again, if you remember, we said that an electric field is going to generate a force on a charged particle. So a magnetic field is also going to generate a force on a charged particle. So we're going to look at the magnetic force that is generated by a charged particle that has a charge Q. And we're going to see that the magnetic force is going to be proportional to the charge. And the magnetic force on the negative charge is going to be directed opposite to the force on a positive charge moving in the same direction. And the magnetic force is going to be proportional to the magnitude of the magnetic field vector. So the magnetic field vector is going to be represented by this symbol right here, is B. So if you remember, we said the electric field is E, the magnetic field is B. So it's a vector quantity. All right. So now we're going to look at the magnetic force on a charged particle. So generally, the magnetic force on a charge is given by this equation. It's the magnitude of the charge times the cross product of the velocity vector of the charge and the magnetic field vector. So what this picture shows you, if you have a charged particle that is moving with some velocity v, this is the velocity vector, and this is the magnetic field vector, then the cross product of the velocity vector and the magnetic field vector tells me that you get a force that is perpendicular to this plane. So it's at 90 degrees with respect to the velocity and the magnetic field vectors. Now, we can do the same application here by looking at a positive and a negative charge. So suppose that you have a magnetic field that is pointing in this direction here, so the green arrows, and you have a velocity that is going up. Then if you take the cross of the velocity and the magnetic field, you get a force that is pointing in that direction right there. Now, because if this is a positive charge, then Q is positive, it means that the force is going to be pointing in that direction. Now notice that if you have a negative charge, you just need to reverse the direction of the force, because for a negative charge, Q is negative. So if you put Q right there, you just multiply this by -1, you get a force that is pointing in the opposite direction. Now I want to talk a little bit about the vector products. So this is just like a review. So something that you should remember is that if you take the cross product of vector I and vector I, it should be equal to the cross product of J and J, which is K, and this is equal to 0. Now if you take I and J, it's equals to -J and I, which is K, and so on. So generally, this picture here is like something that is going to help you to remember the rules. So if you move in the counterclockwise direction, so if you do in the counterclockwise, if you do I and j, so I cross j is k, j cross k is I, and k cross I is j. Now, if you move in the clockwise direction, so for example, if you do j cross I, then you get negative k. So this is something that you can use to remember exactly how to do cross products. Also notice that the cross product of two vectors can be calculated using this by taking the determinant. So for example, if you do a cross b, you can write it in this form. So again, this is just a review. All right. Now there is something that is called the right-hand rule that you can use to get the direction of the force. So what the right-hand rule tells me is that if you know the direction of the velocity vector, and if you know the direction of the magnetic field vector, then you can determine the direction of the force by using the right-hand rule. So in this example, what you're going to do is that you place your fingers in the direction of the velocity field vector, and then you curl your fingers in the direction of the magnetic fields. And so once you do that, then your thumb is going to tell me the direction of the force on the charged particle. So again, this is how we compute the force. So the magnetic force is just the charge times the cross product of the velocity vector and the magnetic field vector. So remember that the electric force is given by this equation. It's just the charge times the electric field. All right. So again, this is just like an alternative right-hand rule here. So you can also place your thumb in the direction of the velocity vector, and then you place the rest of your fingers in the direction of the magnetic field vector. Then the force is going to be pointing out of the board. So notice that when your fingers are, when your hand is placed in such a way that your fingers, so your palm is open, then it means that the force is pointing out of the board. All right. So now we're going to look at this example here. So basically, if you take the cross product of two vectors, so v cross b, then the magnitude can be written like this. It's the magnitude of the charge times the velocity times the b field times the sine of the angle, where the angle is just the direction between the velocity vector and the magnetic field vector. So we can use this equation to get the magnitude of the force, and then we can use the right-hand rule to get the direction of the force. So this table shows you some examples of some types of magnetic fields. So for example, the magnetic field produced by the Earth is about 5 times 10 to the negative 5 teslas. The magnetic field used in the hospital to produce the magnetic resonance image is about 1.5 teslas. So the unit for magnetic field is going to be measured in teslas. So this is just showing you some examples of different types of magnetic fields and what their strengths are. All right, so also notice that 1 Tesla is just 1 Newton per amp per meter. And there is a different unit that is called the Gauss. So 1 Tesla is about 10 to the power 4 Gauss, but the standard unit is the Teslas. All right, I'll leave this quiz. So this is a quiz that I'll let you guys take a look at that. Now let's look at this table right here. So this table kind of gives you like a comparison of electric and magnetic fields. So you can see that the electric force vector always points in the direction of the magnetic field, points in the direction of the electric field, while the magnetic force vector is at 90 degrees with respect to the direction of the magnetic field. The electric force always acts on the charged particle regardless of whether the particle is moving or not. But a magnetic field is only going to act on the charged particle when the charged particle is in motion. An electric force is going to do work in displacing a charged particle. A magnetic field does not produce any work when the velocity of the charged particle is at 90 degrees with respect to the direction of the magnetic field. We'll talk about this a little bit later. All right. So now we're going to look at one example here. So again, we're going to use this equation here to calculate the magnetic force on a charged particle if we know what the velocity of the charged particle is and if we know what the strength of the magnetic field vector is. So let's look at this example right here. So in this example, it tells us that an electron moves in a region with the velocity that is given by 8.0 times 10 to the power 6 meters per second. And the electron is moving along the x direction right here. Then it tells us that there is a magnetic field that is in the xy plane, makes an angle of 60 degrees with respect to the x-axis. And I want to calculate the force on that electron. So I can calculate the magnitude of the force using this equation. It's just the magnitude of the charge times the velocity times the strength of the magnetic field times the sine of the angle. So notice that the velocity vector, there is a 60 degrees angle between the velocity vector and the magnetic field vector. So you do sine of 60 here. You get the magnitude of the force, which is 5.5 times 10 to the negative 7. Now, if you want to get the direction of the force, you can use the right-hand rule. So in the right-hand rule, you place your thumb in the direction of the velocity vector, and then you just place the rest of your fingers in this direction of the B field vector. Then you curl your fingers in that direction. It tells you what the force is. So notice that because an electron is negative, then you get a force that is pointing down. Now, generally, you can solve this equation here using vectors. So for example, you can write what the velocity vector is. So the velocity vector is 8.0 times 10 to the 6 meters per second. It's pointing the I direction. And the magnetic field vector is given by 5.0 times 10 to the negative 5 Teslas. Now, because this is at 60 degrees, then the unit vector, so you can write the unit vector in this direction as cosine of 60i plus sine of 60j. And so if you do everything and you calculate the cross product here, you get a force that is equal to negative 5.5 times 10 to the negative 17 Newton pointing in the k direction. So if you're going to use the cross product, you don't need to worry about the right-hand rule, because by taking the cross product, it tells you exactly what the direction of the force is.